In the last lesson, we went through the scenarios of too slow, too fast, and just right for vertical circles. And now I'm going to kind of go through that again. There's going to be some review here, but I'll also add some other features of these particular situations just to help clarify some things. So we're going to start with the Ferris wheel. We're having a good time on the Ferris wheel. Now, it's a slow speed. The centripetal force is small, so I'm showing it there up at the top or at the bottom. It's going to be the same size either place because the speed is constant. The real forces are gravity and the seat normal force. Now, you know a Ferris wheel moves slow, right? And compared to your normal weight on a Ferris wheel, how do you feel? Well, maybe that is a little hard to visualize because it's moving so slow. But I'll tell you what the reality should be. You should feel lighter at the top and heavier at the bottom. And the reason why is because your sensation of weight, again, is based on the support force. So what does the support force look like here up at the top and at the bottom? And we'll consider the side as well. So the sum of the forces as vectors is just the gravity and seat or support force, and that's Fc as a vector. This is not the magnitude equation. The magnitude equation takes a different character. It includes adding or subtracting forces based on their direction. So the Ferris wheel is moving at a constant speed. So Fc is a constant because what is Fc? mv squared over r. And since v is constant, Fc is constant. So that's something to keep in mind over this entire path, any place you are on the Ferris wheel. The seat force basically just has to adjust itself to make it all work out correctly so that when you add it to gravity, you get the centripetal force. So let's look at the top. So up at the top, you have the centripetal force. It's a given based on your speed, and it's inwards. We know that's the resultant force. And it includes mg, and it includes fs. When we add these forces, mg, we have fs, and we see how the addition of these gives us fc. Starting at the beginning, unconnected tail of the first to the unconnected tip of the last. My goodness, what's going on out there? There's some kind of a hurricane or something. Things are bashing around and it's raining and feels like the house is going to come down. Well, if it does, I'll keep recording. We'll just go right through it, right through the storm. Let's see, at the bottom. So what's going on at the bottom? You have Fc being the same thing because you're going the same speed, but it's inward, so it's up. How does that change the vectors? Well, weight isn't changed. It's your weight. What about the support force or seat force? I put a question mark there. Did I draw that correctly? We can solve for the seat force, which again gives the sensation of weight, by satisfying the condition, namely that the vectors add to Fc. Mg hasn't changed. I'm going to go ahead and put the resultant in now. This is the resultant, Fc. So I'm going to add a vector to mg, namely the support force, so that it gives us that resultant. And that means there it is. So we recognize at the bottom, and from the analysis we did a couple lessons ago, that Fs, the support force, has to overcome the weight and provide the centripetal force. So here you see it being larger. Notice it's bigger than up at the top. So this is a manifestation of your sensation of weight, smaller than it is over here. So at the bottom you feel heavier. Hopefully that makes some sense now. Let's look at the side. Looking at the side, we have the centripetal force acting inward. And now we know gravity. And so what about, let's see, we have to add a force to that so we get this. What is that going to look like? Is it going to look something like this? Well, let's see. We can find it specifically by being a little more careful about this. There is one known force, the weight. We know the resultant is Fc there. So let's add a vector onto this vector. Vector addition will give us centripetal force. So there is the specific support force that'll solve the problem. This is a vector representing your feeling of weight at the side. Notice that the vertical part is just canceling the weight. And then there's a horizontal part that gives you the centripetal force. So we won't deal with this too much quantitatively, but it's good to understand. Whoa! A little thunder out there, and recognize that that is your resultant, this is your support force that solves the problem, giving you a net force of Fc. And now we come again to the too fast roller coaster loop, which is designed to keep you in your seat. Thank you, physics. You don't come out of the seat, which may still be a little mysterious to you since the real forces are all acting downward. Why do you stay in your seat? Well, I'll tell you the answer. It's because gravity isn't enough to provide the centripetal force. It needs an additional force downward, namely the seat pressing into you. And if the seat's pressing into you, then how in the world could you come out of the seat? Now that may not have clarified it for you at this point, but I think before we're done, in our discussions of these vertical circles, you'll understand. Well, the real forces acting are gravity and the seat normal. So, considering the top, here we have mg up at the top, acting down on you. And let's go ahead and recognize we're going fast. So Fc turns out to be bigger than the gravity. And that additional requirement is provided by the seat force. So at the top, mg and Fs are in the same direction. So Fs is small in order to provide the required Fc. Gravity's doing a lot of it. Fs needs to do the rest to provide the centripetal force at that speed. At the bottom, mg, downward again, and the centripetal force is upward. The net force has got to be upward. How do you get that? By having a large support force, overcoming gravity and providing all the centripetal force. Now, that is a pretty big support force. So you may feel really heavy at the bottom. mg and Fs at the bottom are in opposite directions. So Fs is large in order to provide the required centripetal force. Now, if you're understanding this well, you may recognize that my statement here is not very tight. Namely, by saying Fs is small, well, it doesn't have to be, because what if Fc is all the way down here? In other words, you're going so fast, you're going twice as fast. Then Fs may have to, in fact, be large in order to provide, in addition to gravity, all of that large Fc that results. But it is true that no matter what, you're going even faster down here, generally. And so the Fs, for a couple of reasons, is going to be considerably larger than the Fs here, even though this Fs could be fairly large. All right. Now, the roller coaster dipper hump. You're designed to feel weightless. So here at the bottom, let's consider that first. At the bottom, we've already gone through this scenario. It's always the same at the bottom. Fc is inward, which is up in this case. So we have gravity, which acts the opposite way, down. And the result is Fc, upward. So we have a support force that does the job for us. Now up at the top, it's designed in such a way that the Fc, the sum of the forces acting down, is uniquely provided by gravity, because the support force is 0. So this is actually the real force that provides Fc. The just right speed? What is the just right speed? It's easy to calculate because the sum of the forces is Fc. And the sum of those forces is mg. So mg is mv squared over r. M's go away. And so we have the just right speed. And there it is, square root of RG. The just right speed where you float over the hump. You could be on an inside loop even and have that speed of rad RG. And you would just float around the inside of the loop without falling down, without separating from the inside of the loop and coming off. So that's a kind of a special speed for this particular scenario. Let's take a couple minutes and just summarize a few of these ideas here. I want to make a point that you don't have to memorize those magnitude equations. I mean, you should recognize that FC as a vector is Fg plus F support as a vector equation. But don't memorize the magnitude equations. Ask yourself instead, what scenario do I have? Is the VCM too slow, too fast, or just right? And then is the object at top, bottom, or side? Get an idea of where you're at. Sketch the force vectors acting on the object, the real forces. Then add them tail to tip to get FC toward the center. Then use vector addition to get the magnitude equation. Basically looking to see which direction the real forces are acting compared to FC. So FC will equal something plus something or something minus something. Okay? And those somethings are generally the support force and gravity. And then solve for the unknown by plugging and chugging. So that's it in a nutshell. And let me just comment also on apparent weight. So I've already mentioned it, but just to clarify, it is your support force. It's not your true weight. Your true weight is actually the force of gravity acting on you. It's a non-contact force. You always feel contact forces. Apparent weight is the contact force that supports you. So apparent weight is F support. Consider being in an elevator. I'm sure you've all had this experience. If an elevator is accelerating upward, usually it just accelerates upward at the first initial moment, and then it's moving at a constant speed. But you feel a jerk? You feel a jerk, you might feel your body go down a little bit. Unless you're in the elevator in such a building as the Sears Tower, which accelerates for quite a while. It's a momentary impulse that hits you, that makes you kind of, well, feel heavier than normal. Because the upward force of the floor pushing on you has got to be greater than the force of gravity down. This upward force has to overcome gravity and accelerate you upward momentarily. So the floor force in that case is your apparent weight. You feel heavier. If you're going up then, and then the elevator stops, momentarily it slows down and you feel lighter. And the reason is because the floor force now reduces a little bit. It's less than gravity, so gravity is winning and accelerating downward to slow you down a little bit. But again, the floor force is your apparent weight, which is less. For vertical circular motion, F support equals apparent weight. Same thing. At the bottom, in vertical circular motion, you always feel heavier because your support force has the job of overcoming gravity and so providing the centripetal force. And at the top, you feel lighter if it's a too slow situation. Now, too fast is a little more complex. You feel heavier or lighter. It can be either. Because the support force can be still really big, so it's bigger than your normal weight, or it can be just a little tiny bit bigger than, just a little tiny force added to gravity, gravitational tug, to give you the centripetal force needed. So in other words, in the too fast scenario, the support force can be any old size. Just right, however, you feel weightless. Why? Because the support force is gone. So that's a summary of the scenarios. And I hope you're feeling a little more confident about how this all works. And utilizing the principles we just went over, you'll be able to solve essentially all the problems in circular motion, the various scenarios that I will challenge you to solve. So good luck with that, and let's have a good time doing it.